Okay, so hi everyone, Senan this side, and in this video we are going to solve this shortest path in undirected graph. So this is not a Dijkstra's algorithm video. You can use that. It's not that. I'll cover that in my next video. But what you are given is in this is that the edge weights are exactly 1. So that is what we are going to use. The logic would be based on this fact that the edge weights are positive and 1 exactly. Now what do you have to do is, given these edges, you have to, given for this graph, you have to mark the weights for each of these nodes, or basically the cost to reach that node using the edge weights from the source. So since the edge weights are exactly 1, whenever you reach a node for the very first time, that would be the shortest path to reach that. Why? Because since the source in this case is 0, so the distance to itself is 0. So you see the 0. Now all the neighbors of the 0 which are not visited are 1 and 3, and both have a distance of 1. So 1 and 3 have a distance of 1. Now the neighbors which are not visited of this 1 and 3, which is 2 and 4, have a distance of 2. 2 and 4 have a distance of 2. Now all the neighbors of 2 and 4 which are not visited yet have the depth or the path length as 3. So 5 and 6 are marked as 3. Now all the neighbors which are not visited of 5 and 6 should be marked with the distance 7, or distance 4, not 7. 7 and 8 are marked as 4. In this case we have a distance of 1 for 0 and 1, distance 1. For the node 3 itself, the distance is 0, and there is no node 2, so the distance to that is -1. So we got this. How we actually do this is by using a breadth first search approach, right? And it's more closely related to the multi-source breadth first. It's like that. So what I do is, first of all, I need to have this graph in an adjacency list or adjacency matrix, because I know how to traverse it more easily. So what I do is create a vector of vector int that makes me the adjacency list, and I get out all the edges, and I mark and I add. For S I would add E, so start and end. I would mark for the, so I'm basically saying that from S there is an edge to E, and from E there is an edge to S. Now I would create a distance array. So by this point of time I have my matrix, or I have my adjacency list, or the matrix where you are comfortable with, and I would define the distance of source to be 0, and I would push that into my queue. Now what I would do, I would initialize a depth. The only reason I am able to do this because the edge weights are 1, and in this type of graph, whenever you reach a node for the very first time, the depth would be that is the shortest distance from the source to that element. Now what I do is, for all the elements in the queue, I take them out one by one, and I push the, so if I have not seen that node before, that means it's not visited, that means the distance of element is -1. I take that into my queue, and I update the distance of that element to the depth, right? This is me basically doing. For 0 I push 1 and 3, and I pop out 0. For this I would push 2 and 4, and I would pop out 1 and 3, and again after this I would push 6 and 5 and pop out 4 and 2. After this I would push 7 and 8 and pop 5 and 6. This is what we are trying to do, and iteratively I would be increasing the value of depth by 1. And let's say if the edge weight of each and every node was exactly the same, you would just increment. Let's say the edge weights was not 1 but 2, or let's say 7. You initialize that depth with 7, and you increment depth is equal to depth plus 7, but the edge weights are 1. We are taking, so that is why we are doing depth plus plus, and we do this till the time we have not visited each and every node that are connected with the source node. And in the end I would return this distance array. The other way to do this is by using Dijkstra's algorithm, in that you would have a queue of pairs, right? The current node and the distance, the max or the minimum distance we have found till now. The logic would be something like that, but since the edge weight is exactly 1, as I'm saying this for the not very first time but the third time, we don't need. So what is the space complexity? Space complexity would be space required to store this vector, that is 2 times edge, and storing the array we have complexity of big O of n, that is number of nodes, and the time complexity for this breadth first search approach is v plus 2e. V is vertices, that is n, and number of edges, that is m, so big O of n plus m, the time and space complexity for this question. So that is the whole video about. Hope you understood this, and I would see you in the next video with the Dijkstra's algorithm. Thanks for watching, and